All right, so let's take a look at this example. We want to see if we can solve for our integrals, but we want to see if we can solve it by doing what we call trig substitution, okay? So when you look at your problem originally, you don't exactly see any trig functions in there at all. But we're going to use this little table over here to kind of help us to see how could we possibly rewrite it such that we do have a trig function in there. So if you take a look at what we have here, you can see we have this 441, and then we have this x squared in there, okay? So we have a number minus an x squared. So when you take a look at this first um, piece here in this nice table that's going to help us, you can see we have an a squared minus x squared, and it's under the radical. So if we look at our original problem, let's see if we can figure out how to rewrite that 441, okay? Well, that's a nice perfect square, and we know the square root of 441 is just 21. So we have something that's going to be similar to this first setup here, the square root of a squared minus x squared. And so then what we're going to do is then we're going to look at the corresponding substitution. So we're going to replace x with our a times sine of theta. And remember, your a is 21. So let's see how can we rewrite this integral, okay? So again, we're going to let our x be equal to our a, which is 21 times sine theta. And then if we have that as our x, then our derivative of that would just simply be, we have that 21 in front, just bring that constant down, and then the derivative of cosine of sine is cosine, okay? So now we have our x dx. So let's see then, how can we rewrite this integral here, okay? So then we have the integral. Instead of now writing that square root of 441 minus x squared, in the place of x, we're going to write 21 times sine. So we have the square root 441 minus, okay, so again in the place of x, we're going to put what we had it equal to. All right, and then in the bottom, okay, we said that's also divided by x, so divide that by 21 sine theta, and then times our dx, okay? Well, remember we said dx was just 21 times cosine theta, and then don't forget to put the d theta. All right, well, let's see then what can we do from here. So let's go ahead and simply square that 21 sine squared, and when we do that, we have the square root of 441 minus, well, 21 squared, that's just 441. And then sine squared, so we're just going to simply write it like so. And then that's all under the radical. And then we're going to keep the denominator as it is. And we still have this times 21 cosine d theta. Okay? Well, if you notice under the radical, we have a 441 here and a 441 there. And what we're going to do is we're going to factor out a 441. So we end up with the square root of 441. Then we have 1 minus sine squared left over. So we now have that under the radical. Okay, then everything else stays the same for now. All right, well, if you remember a nice Pythagorean identity, right, we can rewrite that 1 minus sine squared. So we're going to write that as 441 times cosine squared, all under the radical. And then everything else still remaining the same for now. Okay, well now let's simplify what we have here. Okay, so we now want to take the square root of 441, and we also can take the square root of this cosine squared. Okay, so that's going to give us 21 times just the cosine now, because that canceled out with the square. And then we have the 21 sine theta times the 21 cosine theta d theta. Okay, well, let's see, what do we have here? So if we go ahead and multiply what we have in the numerator, then we have 21 times cosine squared over this 21 sine theta d theta. And then we're just simply going to use another Pythagorean identity. So instead of having this cosine squared, we're going to kind of use the Pythagorean identity once more. So we have the integral of 21 times 1 minus sine squared theta and then over our 21 sine theta d theta. Okay. All right, so now since we have that minus there, we're going to go ahead and split our integral. So we're going to make it 21 over our 21 sine theta d theta, then minus 21. And then if you notice here, I have a sine squared over another sine, so we really could have just wrote sine theta, okay? All right, so then what do we get? We have, if you think about your 21 right here, we're going to pull it out to the front, and then we're going to see if we can rewrite that trig identity. Instead of 1 over sine, we're going to make it 1 over cosecant, okay? All right, and let's see. Since we had to go ahead and distribute this 21 here and this 21 there, then technically we can see that it looks like the 21s would cancel, but if we actually go back here to this step, we actually forgot to either multiply those two together or cancel one of those 21s. So if we do that, then we really don't have a 21 here in the bottom. Okay, so that means I can take this 21 off here. Okay. All right, so now I got a 21, and then I'm rewriting my 1 over sine. I'm going to write that as cosecant theta. And then minus, and then here with my other integral, I just have a sine theta. Okay. All right, and so now from here, we will use our integral rule. So you may have to refer back to your formula sheet, okay? So you would see that the integral of cosecant is actually going to be the natural log of cosecant plus cotangent, okay? So we still got that 21 in the front, and then it's actually going to be times negative 1 over a, right? Your a in this case is just understood 1. So natural log, absolute value of cosecant theta plus cotangent theta. All right, and then minus, now we have to take care of this other integral over here. And so we have that 21 in front, and then we know the integral of sine is just negative cosine. Okay, then we have the plus c. So if we put this together, what do we have? Well, here we have this negative 21, but what we're going to do now is see if we can kind of rewrite our cosecant and our cotangent. Okay, so we're going to try to rewrite cosecant and cotangent, all right, in terms of our original problem, okay? So let's make a little note here. All right, so this is where we left off with the previous problem. So now let's see, how can we rewrite our trig functions back in terms of the original problem, okay? So remember we did our trig substitution, so now we have to replace it back as if we were doing the same with the u substitution, okay? Well, let's kind of make a note to see how we're going to do this, okay? If you think about, we have a nice triangle. We know we use a right triangle a lot when we're talking about these trig functions, trying to figure out what they are. So let's suppose I have an angle here, okay? Well, remember in the beginning, we said we let our x be that 21 sine theta, right? And so if we were trying to solve for sine to get sine by itself, then we would just simply divide both sides by 21, okay? Well, if you remember your SOHCAHTOA, how to label everything, all of your sides on your triangle, then we know sine is just opposite over hypotenuse, okay? Well, to find the missing side right here, we know we would just simply do the Pythagorean theorem, right? And you would see that this missing side would be the square root of 441 minus x squared, okay? Well, that looks familiar, right? That's what the beginning of our original problem had in the numerator, okay? So what we're going to do then is we're going to come over here and rewrite everything using that triangle. Okay, rewriting it using this trig function. So we end up getting negative 21 natural log absolute value of, okay? Well, we know cosecant. Cosecant is just 1 over sine, okay? Well, we know what sine is, x over 21. So that's just simply going to be 21 over x, okay? Just a reciprocal of that. Plus our cotangent, right? We know tangent is opposite over adjacent, okay? So then cotangent is going to be adjacent over opposite, okay? So therefore it's the square root of 441 minus x squared over x, okay? So all that came from using the triangle there. Then plus 21, now do our cosine. Well, we know the cosine is just simply adjacent over hypotenuse. So that's the square root of 441 minus x squared. So let's make this a better 441 minus the x squared. All right, all over our 21. Okay, and then we still have the plus c. All right, so there you go. We basically have done everything that we needed to do. So if we wanted to stop there, we very well could. But since we have the same denominator here, let's go ahead and put those together. And technically, since we have this minus here, you really want to kind of apply the power rule. But here we're just going to kind of do the basics here. We're going to kind of leave that negative 21 in the front, and then make this 21 plus the square root of 441 minus x squared, so the square root of that all over x, and then plus, then of course you can see here your 21s cancel out, so square root 441 minus x squared plus c. All right, and there we go. Okay, so that's how we would apply trig substitution instead of u substitution for that one. All right, so again, we want to see if we can try to evaluate this using trig substitution, okay? So you can see there's absolutely no trig at all in the function, but we have some nice little features that we can kind of use from this table to see how can we apply the trig substitution. So if you see in this case, we have a perfect square 9, so our a must be 3. So we have an a squared plus x squared, okay? So this time we're going to be using our trig function tangent to do our substitution, okay? So our a in this case is 3. So what we're going to do is we're going to let our x be 3 tangent theta. So therefore our dx is just simply 3 secant squared theta, okay? The derivative of tangent is secant squared, all right? Well, since we have bounds this time, all right, we're going to have to kind of see if we can switch those in terms of the unit circle, right? So what we're going to do is, since we have x is equal to that, where if we were trying to get our theta by itself, then first we would divide both sides by the 3, and then to get the tangent by itself, we would have to take the tangent inverse of both sides, okay? So we can rewrite theta like so. So now, let's see if we can do our bounds, okay? So first, we have the upper bound, right? Or let's do the lower bound. First, the lower bound is 3 over the square root of x, okay? Well, taking what we know about our theta over here, then if we say theta is equal to tangent inverse, all right, of just x over 3, then if we think about what we have here for x, so if we were to get x over 3, that means we're dividing both sides over here by 3. And therefore, tangent inverse, we can rewrite this as 1 over the square root of 3, okay? So that's just simply dividing both sides by 3, okay? Then from here, we would go to the unit circle, right? And we would get tangent must be pi over 6, okay? So remember, from the unit circle, okay, if we have 1/2 over the square root of 3 over 2, that's the same as 1 over root 3. And then, so we know that's the sine over cosine, right? And so we go to the unit circle. So that's how we get this pi over 6, okay? All right, and then let's do the upper bound, right? So here x is equal to 3. Then again, taking what we know about our theta, we have tangent inverse of x over 3. So therefore, we can rewrite this as tangent of 1, okay? And again, that's just simply dividing both sides here by 3, okay? That's how we get the 1. All right, and so anytime you have that 1 there, that means your sine and your cosine must both be the same. So we can see at pi over 4, that's when they're both the same. All right, so now we are ready to rewrite our integral, okay? So we're going to rewrite our integral here, okay? So now we have the lower bound is pi over 6, and the upper bound is pi over 4. All right, now let's think about what we have, okay? We have the 7 that was here, so we're going to write the 7. All right, well then, what did we say our dx was, right? We said dx was this, okay? So we're going to rewrite that. So 3 secant squared theta, okay, then d theta. All right, well, what did we say about what we have here in the denominator? Okay, well, we said x was equal to this, so we're going to square that, and then we're also going to replace this x as well. All right, so therefore, we got 3 times tangent theta squared, all right, and then that's times the square root of 9 plus tangent theta squared, okay? So that was replacing everything using our trig substitution, okay? All right, so now let's see if we can kind of simplify this out just a little bit. So here in the numerator, 7 times that 3, I'm going to get 21 secant squared. Then in the bottom here, go ahead and square that out, right? So that's going to give us 9 tangent squared theta. And then this was under the radical, so then that stays, oh, and don't forget, we were supposed to put a 3 right here, okay? So therefore times 9 plus, and then square this 3 tangent squared theta, okay? All under the radical, okay? And then our bounds stay the same, okay? All right, so now let's see, what do we have here, okay? So if we want, we can go ahead and we see that we have a 9 here and a 9 here. So we're going to factor out a 9 there. And then you're going to see that we have a 1 minus tangent squared, okay? So we're going to leave the numerator 21 secant squared theta. And then in the bottom, we have our 9 times tangent squared theta. And then factoring out the 1, you'll see that we get the 1 minus tangent squared theta. Okay? All right, well, remember we can use a trig identity, Pythagorean identity for that. Okay, so everything's going to remain the same for now. Okay, and then we have times the square root of 9 times secant squared theta. Okay, all right, well, let's see then. What can we do from here? Well, we can see that we have the square root of 9, square root of secant squared. So that's going to simplify to 3 times secant, right? And then we have this other 3 out here, or this other 9. So we're going to multiply the 9 times the 3, okay? So let's see what we have inside of the integral. Okay, so we got 21 secant squared theta over. So remember, this is the square root of 9 here, which is 3 times this 9. So 27. Then we got tangent squared theta, and then just secant theta because of the square root, okay? All right, well, you can start seeing that this secant is going to cancel with this secant, okay? And then we have this 21 over this 27, so we're going to simplify that. Okay, that'll simplify to 7 over 9, right? So we're going to bring that out in front of the integral. So we're just left with a secant theta over a tangent squared theta, d theta, okay? All right, and so now from here, we're just going to simply rewrite our secant and rewrite our tangent in terms of its reciprocal identities. All right, so now continuing from that last line, we now want to see if we can rewrite our secant and our tangent in terms of sine and cosine. So we have our 7 over 9 out in the front. We got our bounds. And now the reciprocal identity for secant, we know that's just 1 over cosine. And then we can rewrite tangent as sine over cosine. But since it's tangent squared, we got to remember to put a square on both the sine and the cosine. All right, so now if we simplify, we got a fraction over fraction. So of course we can take the fraction in your numerator and multiply it by the fraction in your denominator, by the reciprocal of the denominator. Then that's just simply going to give us cosine over sine squared, okay? All right, so again, taking the top fraction and multiplying by the reciprocal, and you'll see how that cancels out. So now, from here, we want to see if we can try to apply u substitution with this part. So, of course, we got that sign in the denominator, so let's let u be that. So therefore, if we find the derivative of sine, we know that's cosine, okay? All right, well, let's then rewrite our integral in terms of u and du. So our cosine theta, d theta, all of that was our du, and then with the sine, right, we have that's our u, and then we have a square on that. So we can just simply rewrite that as 1 over u squared du, okay? Then, of course, we can rewrite that, kind of bringing that square up to the top, making the u to the negative 2 du. All right, so now we're ready to integrate. So we got 7 over 9. That now becomes u to the negative 1 over negative 1, and now we are evaluating from pi over 6 to pi over 4, okay? All right, so we can kind of rewrite that just a little bit, just so that we can bring that u back down. All right, well now, if you remember, we did change variables, but we didn't change the bound, so that means we gotta now remember to plug our u back in. Okay, so we said u was sine, so we got to put that back in for u. Okay, all right, so when we do that, we have going to go ahead and bring this negative out with this 7 over 9, and now plugging in your upper bound with that u plugged in, so the upper bound pi over 4, then minus, now plugging in your lower bound pi over 6. Okay, all right, and then of course from here we would just go to the unit circle, right, so that we would know what sine of pi over 4 is and sine of pi over 6, okay? So sine of pi over 4, that's just simply root 2 over 2. Sine of pi over 6, that's just simply 1/2, okay? All right, so simplifying those fractions inside, then 1 over root 2 over 2, that just becomes 2 over root 2, and then 1 over 1/2, that just becomes 2. All right, and so now from here we can go ahead and distribute our negative 7 over 9 through. And so when we do that, we end up with negative 14 over 9 root 2 plus 14 over 9, okay? All right, and so from here, right, we know we want to rationalize the denominator, so we're going to have to multiply the top and the bottom by root 2 because we don't want to leave that radical in the bottom. So we end up getting 14 root 2 over 9 times 2, right, because root 2 times root 2 is just 2. Then we still have this plus 14 over 9 here. All right, so put it all together for our final answer. We can go ahead and simplify here the 14 over the 2. So we end up with negative 7 root 2 plus 14, and then they have the same denominator, so you can kind of put it all together all over 9. And there we go. So that would be our final answer.